I wanted to go over our star shot analysis with you today. And the star shot analysis is located under the beam measurements menu. And the star shot analysis that we have that we're going to go through in this section is based on film measurements. So we do have some other star shot routines. We have a virtual star shot under the 3D EPID stereo tactic alignment. So if you want to do a star shot with your EPID, we can certainly accommodate that under the 3D stereo alignment routine. But for now, let's look at basically film-based star shots, although you might be able to do some of these with an EPID, just not as easily as with the new 3D stereo EPID tests. So if I open up the star shot routine, the first thing it wants me to do is to give it a sample file. And so if I go to star shot, what I've done here is I've gone to the RIT directory on my C drive, and I've gone to the 113v4 directory, and in demo images, we're going to the star shot routine. So if I look at the demo images, there are a couple different star shot images that we have there, and I'm going to open up the one that's called full star. Okay, so this is a film that we've taken and scanned on a VIDAR scanner. We could also have scanned it on a flatbed. That wouldn't make any difference. We've associated this with a calibration file, so it's coming in calibrated. So you can see that the minimum dose on it is about 2.3 centigrade, and the maximum dose here where the beams intersect is about 18 centigrade. Now, the star shot analysis routine is going to go in and try to find each one of these beams. In order for that to do that correctly, we can't have any writing or other marks on the film. So if you do have writing or other marks on the film, it's usually a good idea to go under the Edit menu and use the Erase and Pinprick tool in order to remove those. We won't use the pinprick part of it, but we might use the erase part of it. Another thing that's critical about this test is that for the region of interest that we're going to select here, we have to make sure that each one of the beams goes all the way to the edge of the image. So if you have maybe a piece of film that was sticking out of the phantom, and maybe there's a very light edge up here where it was fluences compared to the dose that might be in the slabs of solid water that we're taking here, we would want to crop that. And sometimes when we're measuring beams, the beam might not go all the way to the edge. Now this is a gantry star shot, and so this film is perpendicular to the gantry. So it's pretty easy to get all of these going all the way to the edge. However, if you were to do a collimator star shot or a table star shot, it may be that you would have beams in there that only went through part of the piece of film here. And so with that, you would want to crop those using the Select Region of Interest tool and go in and crop those in a way so that all the beams made it all the way to the edge of the film, and that they looked fairly uniform, that they weren't, like I said, if they were sticking out of the solid water, they might be very, very light up here. So you can use the Region of Interest tool to make sure that it's uniform like this, so that the beams are going all the way out to the edges. Typically in a piece of film, we would apply a median 5x5 filter, and a median 5x5 filter goes in and removes any lint or dust or fingerprints that might be on this film, or even small scratches. So that can be very useful in the film analysis of this star shot. So now that we have the image and it's ready to be analyzed, we can look at the star shot analysis area over here, and it will say that we have to specify how many legs are in this pattern, and the number of legs is twice the number of beams. So if you thought of this more, instead of a star shot, more like a starfish, and we saw that each one of these was a leg that was coming out, then these are the legs that we're trying to define here. So the legs are twice the number of beams, since on every beam we've got an input and an output here through the center of the film. There's also a threshold, and 20 seems to work very, very well for almost all of our customers. Occasionally, you might get a message from the software that would say that it can't find one or more beams. So we've told it here that there should be 18 legs or 9 beams here, and if it can't find one or more of these, it will give you a warning message about that, and then you may have to adjust the threshold in order to let it go ahead and find all the legs that you've specified. The only other reason why it might not find a leg is if there were some writing or some other marks on the film where it was incorrectly cropped. So that could be something else you might want to try if you get that warning message. So now all we have to do is click Analyze Image, and it's gone ahead and done this star shot analysis all automatically for us. We can see here that it's outlined the edges of each one of the legs with a dashed line. We've got a solid line for where it determines the center of the beam, and then we have where all the beams intersect. Now this is a this analysis window is showing us quite a bit of data, and we probably don't need all of this. For instance, if you're doing this to comply with TG 142, the only measurement of these 5 measurements that are here that you would really need is the minimum tangential circle radius. That's why we put in here TG 142. This is the measurement that they're looking for in that task group report. So if that's all I wanted to see, I could go in here and say, I could uncheck some of these other measurements, and now the only thing I would have here is a plot. The points on the plot, the circular points, are the beam center intersections, and the points with a cross through them are the beam edge intersections. Now we don't even need to have all of this other data on the plot if we don't want to. We could take the beam centers out. Actually, that's kind of helpful. Maybe we don't need the beam edges, so we can look at all of those. And for instance, this may be just the data that we want to see here, just the beam center intersections. So this is where the center of each beam intersects with another beam. So this would give us the minimum tangential circle radius as defined in TG 142. Now when we started off with this software many years ago, there was no definition like a minimum tangential circle radius, and so most customers use this ANSI 449 specification, which looks at the maximum circle that it would take to encompass all of the intersections of the beams. And so so this is what it would take here in order to do this, and you could see this is the defining radius here for that. It's not used very much anymore, but we did want to include it because several of our customers still rely on that method. And so it's easier just to uncheck this if you don't want it anymore. There's also a measurement of the maximum perpendicular distance for the circle. You can define the maximum perpendicular distance from a user-defined center, and you can grab this. You can move this center around. I guess you move it over here, and so if there was a mark or something in the center of the film that you wanted to use as a user-defined center, you could do it that way, and then it would give you that information. Now that we have this information, we could go up here and we can save this whole page to a file. It would essentially be a screen capture of this entire page with whatever checkboxes for an analysis that we wanted here. We can also take the results here and copy this to the clipboard in case we wanted to put it into a report. We could print it out if we wanted to, or export this in ASCII format. And if we click on that, then we get all the header information here about what we have analyzed, along with the for each beam the x position where it starts and ends, and the y position where each beam starts and ends, and this intersection position information. And finally, probably the most useful thing in all of this is this icon at the top, which goes ahead and exports the results into the RIT trend database so that you can track this over time, and also set limits and tolerances on this analysis, so you can get some warnings if this should drift out of tolerance on you. So that's the overall demonstration for the star shot. And as I mentioned earlier, you could do this with gantry images, with collimator images, or with couch images, and the star shot information all works the same. Now, if you wanted to do this with, say, a couch star shot, it is possible to go in and under the edit menu, you can use the 113 image compositor. So if you did acquire this for a for a couch or a collimator star shot, and you acquired it on your EPID, you could use the image compositor to go ahead and put together a composite image for you from each of those star shot legs. Let's see if we can go ahead and do that. So I've opened up the image compositor, and I'm going to tell it here that I'm going to bring in some Varian EPID images. This should also support the AS1200 now, but we're just going to bring in DICOM files from these images. And I could either bring in individual images, or I could bring in a directory of the images. So let's see if I can get a directory of those. So if I go to composition examples here, so again, I went to the C drive where I have the RIT software installed. I went to the 113v4 directory, and in demo images there are a number of composition examples. So let's look at this Varian EPID MLC star shot. So by selecting that folder, it's imported all the images in that folder, all of these EPID images, and if I wanted to go down here and click on this icon, I could preview the images. So I can see that the last image looks like this, and the next image looks like this, the next image looks like this one, and the last image looks like that. So now, if I want to composite those, there's a couple different ways I can do that. I could tell it, use a calibration file. So if I have a calibration file, I can go ahead and select that. Now this is from an EPID, so typically from an EPID, we can either use 16-bit invert or invert and scale to range. I'm just going to say invert and scale to range. That would be probably the easiest. You can see here from this image that the background is very high level and the exposed area is a low level. So that's why we want to go ahead and invert this image. The next thing here, we've already selected the images. We could have put some additional scaling on that if we wanted to. We could have set some minimums for the composition value. We could add or remove files or directories here, and we could order these if we want to. In this case, we're going to composite all of them into one star shot, so it's really not necessary to order or sort them at all. But we can go ahead here and now we can select an operation for that. We could add them or subtract them, multiply or divide, or any one of these functions. We're just going to add them all together after they've been inverted and scaled. So the next thing that I have to do here, and really the second to the last thing here, is to tell it where we're going to put this. So if I go in here and I'm going to make a file called sample, and it's going to save this in a MATLAB format for us. And the reason that we're saving it in a MATLAB format is because if we had a number of images with a lot of dose on them, we wouldn't want to exceed the range of the original images. So if we scan these in with, say, a 12-bit scanner, then we would be stuck at having only 12-bit values, and when we added them together we might exceed that range. So because of that, we always make these into MATLAB files when we're done. So now that we've got a path and a file name for this, you see that the create composite is not grayed out anymore, and as soon as I say create composite, it's going to put those all together into this beautiful little star shot for us, and I can close and then load that image and then go through a similar process here. Maybe we should go ahead and do that. So if we have, say, 1, 2, 3, 4, so we have 4 beams, and so we'll have 8 legs, and we'll leave the threshold where it is, but remember that I said that the beams have to make it all the way to the edge, or just about. So now I'm going to select a region of interest, and with this region of interest, I want to try to get it so that this beam is making it to the edge, and the top ones and the bottom ones really aren't so much of a problem. But we'll try to get the rest of the beams to the edge there like this. I don't know if I have to. Well, I think I'm okay doing it that way. And I'll say apply region of interest. So now we have every one of the beams going all the way to the end, and I can say analyze image, and now I have the star shot analysis for this, and you can see what a good star shot it is. It's really down to a very small minimum tangential circle radius for us. So now I could go ahead and save that or drop it into the database, and that would be my analysis. So this is an example of how the star shot works, and also a little bit about how